An Army missile system must be able to take punishment. It must be built to move quickly. Emplacement time must be short. Firing procedures must be simple. The missile must be accurate. And a missile crew must be able to shoot and scoot before an enemy could spot them. To make certain that Army missiles can actually perform as expected is the job of the Ordnance Mission at White Sands Missile Range. Inside at this minute, a briefing is taking place. Let's sit in. The Commanding General of White Sands Missile Range is responsible for providing a well-instrumented range for all three services. As well, he is responsible for engineering, test, and evaluation of all Army missiles assigned here. This last-named responsibility is the prime reason for being of Ordnance Mission. To do this job, our scientists, engineers, and technicians must answer two basic questions. First, how well does the system meet desired military characteristics? Second, what are the limits of performance? This involves both detailed analytical tests of components in the laboratories and overall systems tests, wherein the missile is fired and the entire system is tested as an integrated unit. In addition, we carry out a number of support missions. But before discussing those, let me show you some film on typical Ordnance Mission operations. All right, Sergeant. Much of our ground testing is carried out in these laboratory and technical buildings. Now to take a look inside one of the labs. These lights are being used to bake a powerful adhesive which holds anchoring tabs on a lacrosse missile's outer skin. The steel cables being threaded through the tabs will hold the missile captive for a static firing. This is just one type of the many tests we perform to determine the structural adequacy of critical missile parts. Secured in its restrained firing structure, the lacrosse is on its way to the firing site. At the firing site, Ordnance Mission propulsion experts install the solid propellant motor. On firing day, nearly 40 instrumentation channels are set to collect data on both motor performance and the magnitude and effect of shock and vibration on various structures of the missile. At the firing console, the operator makes ready for the final count.
Attention to firing area. At my mark, time will be X minus 60 seconds. Mark. X minus 60 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Also in connection with stress analysis, we are conducting experiments with polarized light. This is a promising technique for determining direction and magnitude of stresses in missile component materials. For this work, a variety of instruments are used, some long known, others of recent development. Here, using the calibration lab's testing machine, this metal specimen will be subjected to progressively greater tension until the breaking point is reached. Initial load on the specimen is set at 15,000 pounds. $19,000, $20,000, $21,000, $22,000, $23,000, $24,000, $25,000, $26,000, $27,000, $28,500 pounds. Ordnance Mission is equipped for testing any single component or entire guidance and control systems. Here, the Hawk system is subjected to electromagnetic energy in the radar frequencies. The purpose is to determine which frequencies, at what signal strengths, might ignite the firing squib. This knowledge is important, of course, to the using arms. Extensive facilities are available for evaluating missile-borne guidance systems. For example, this 3-axis flight simulator can reproduce all angular motions to which this assembly of sensing devices would be subjected in flight. As many as 52 channels of information can be simultaneously recorded for later analysis. This building houses the latest in flight simulation computing equipment. Inside, electronic circuitry, tubes, and transistors are substituted for launch pads and impact areas, and mathematical expressions for missile hardware. Practically any tactical or environmental condition affecting flight can be simulated. For example, this operation is to determine the effects of strong winds and other aerodynamic factors on the control fins of a particular missile. With amazing speed, the analog computers provide the solutions. This equipment is especially well suited for study of the complex high-speed dynamic functions of missile guidance and control systems. Digital computing equipment is also used for simulated flight analysis. Digital techniques are particularly advantageous when a high degree of accuracy or exact repeatability is required. Simulated flights supply us with hard-to-get data, which become increasingly valuable as they are compared with actual flight test results. Our extensive environmental testing facilities ensure that missile systems can function in unfavorable climates or weather. Besides salt fog, we simulate other natural environments: blowing dust, heavy rainfall, fungus growth, Arctic cold, tropical heat, humidity, solar radiation, and high altitudes. Mobile equipment is used for environmental conditioning at firing sites. Inside this test shroud, a Little John missile is being refrigerated. In seconds after the shroud is removed, the missile will be fired before its temperature rises. scores of test sites scattered over our 4,000 square mile range require a vast variety and number of instruments. A fleet of instrumentation vans ensure that the needed equipment can be speedily dispatched where needed. The skilled technicians who operate the vans provide all types of ground instrumentation. Measurements are made of phenomena such as strains, pressures, forces, and blast effects on missiles, launchers, warheads, and associated equipment. Permanent instrumentation facilities are also maintained. In labs such as this one, scientists and engineers perform research in various fields to design systems or test instruments. Data conversion, storage, demodulation, and presentation equipment, peculiar to lab tests and evaluation of missile systems, are also provided. Missile technology requires a large variety of highly precise measuring equipment. This large balance has a 75-pound capacity with a 65 milligram sensitivity. This contour projector allows close visual inspection of small surface features. A versatile 100-inch mercury column aids in hydraulic pressure measurements, achieving an accuracy as high as 0.1%. Besides these, a multitude of other machines are employed for accurate measurement and calibration. This is the business end of a linear electron accelerator. It is used to subject missile components to gamma radiation. Housed underground and operated by one man for safety, the accelerator determines, in part, how missiles will perform in a nuclear environment. From this console, the radiation is controlled. Inside the accelerator chamber, for demonstration purposes, a piece of lucite undergoes electron bombardment. The electron beam has a peculiar effect on the lucite. Note the strangely tree-like pattern. Nuclear radiation of another type is produced by this pulsed neutron generator. In this area, the component under test is placed. Inside the generator, we see the big acceleration tube in the forefront. The missile component package awaits neutron radiation. A turn of the safety key begins the bombardment. The acceleration tube goes into operation. From this target come the neutrons, which bombard the component. Atop the pole in the foreground, a missile warhead will soon be detonated. This is only one of a variety of warhead tests performed in our hazardous test area. High-speed photography facilitates analysis of results. Here, preparations are underway for detonation of some 40,000 pounds of TNT, sponsored by another service and supported by Ordnance Mission and other Army elements, this series of tests yielded information needed to determine interaction of explosive waves. On test day, in this van, instruments are set. Seconds remain. Not all of our operations are as spectacular. For example, our field service people coordinate and assist in the preparation of the hundreds of publications required to operate and maintain a missile system in the field. And here is produced the end result of our labors, the final technical report, a composite scientific analysis of accuracy and reliability, as well as logistical and operational requirements and procedures. Most of the operations you just saw were analytical tests needed for ordnance engineering evaluation. However, some were performed in carrying out our support missions. Under test plans approved by either the Army Ballistic Missile or Rocket and Guided Missile agencies, we provide the missile developers with engineering, services, and facilities. We attempt to accomplish as many different missions as possible at one and the same time, such as support for user tests, proof testing, industrial engineering, product improvement, surveillance testing, services to Navy and Air Force. And now, here's an example of what I mean. This Honest John is a production line sample, undergoing proof testing to see that original specifications are still being met. Also, the missile is to serve as a target for this surface-to-air Hawk, being prepared by artillery troops for a user test. These tests determine the system's effectiveness under simulated combat conditions. Target is away. The Hawk goes for the kill. This improved version of the Nike Hercules is set to hunt down and destroy a supersonic corporal. The corporal, in turn, is undergoing a surveillance test. On site for many months, this missile has been returned to White Sands, disassembled, examined, and reassembled to see how well it has withstood storage and field conditions. The Nike Hercules is to be fired to test a product improvement instituted by the developing agency. Also, the soundness of industrial engineering changes by missile manufacturers are determined by test firings. The target is set to go. Miles away, downrange, the killer missile streaks for intercept. Gentlemen, you've seen some of the operational highlights of Ordnance Mission, an organization embodying a unique combination of technical talents and facilities. Today, we continue the later stages of testing on such older missiles as the ground-to-air Hawk. surface-to-surface lacrosse. Little John. Redstone. And Sergeant. At the same time, we look forward to progress in newer programs, such as the surface-to-air Red Eye, the surface-to-air Mauler, the surface-to-surface Shillelagh, the Redhead Roadrunner Target Missile, the surface-to-surface Missile A, and finally, the free world's only anti-missile missile currently under development, the Nike Zeus.
7, 6, 5, 4, 3, 2, 1, 0.